Okay, today we're going to talk about the law of conservation of matter, and specifically about the biogeochemical cycles. So we know the law of conservation of matter says that matter cannot be created or destroyed. And that's really important because it lets us know that the amount of carbon and nitrogen and phosphorus and sulfur and even water that's on the planet will continue to be here, just in different forms. And so we want to look at those different forms as those elements cycle through nature. Speaking of biogeochemical cycles, we're going to cover the 5 that you see there on the left. We're going to look at the water cycle, which you've covered for a long time, the carbon cycle, the nitrogen cycle, the phosphorus cycle, and the sulfur cycle. We'll learn about where the major reservoirs, where the holding tanks are for those different elements as they cycle through nature, and why they're important, and how they get from one space to the next as they move through different parts of the cycle. So here's an image of the water cycle, and as you can see, if we were starting, we can start anywhere in any of these cycles and move through the different phases. If we were to start, say, up here in clouds with condensation, the water has just evaporated from the major reservoir for water, which is the oceans in saltwater form. And as it evaporates, it becomes a water vapor, and then it condenses into clouds. As it's a cloud, then it moves onshore or maybe even over the ocean, and it rains precipitation here. Another big reservoir for water on the planet is stored in ice and snow, or glaciers and ice caps. That can melt, or as it falls as rain, the water can run off the land, or maybe even over an impervious surface like cement. And it goes into the watershed, or maybe it's picked up by plants and then eventually sort of like sweated out, or that water is evaporated from the plants through transpiration as those leaves open up for photosynthesis. Another option for water is as it moves to the ground, it can infiltrate in through the different particle layers of the soil and eventually become a groundwater into our storage of groundwater in the aquifers, or eventually maybe discharged back out into the ocean. So as you see here, water comes down as precipitation, it goes into the earth as groundwater, or the oceans, and is taken up by plants. It returns to the air by evaporation, and evaporation can happen not just from large holding tanks for water like oceans and lakes, but evaporation can actually happen from animals like us as we sweat or breathe out. And then transpiration is specifically the water that comes out of plants during photosynthesis. All right, so we know that water is essential to life. In fact, humans going without water, we can only last about 3 days without some form of water, whether it's from what we eat or drink. And lucky for us, the water gets cleaned through the water cycle. As water evaporates, it leaves other stuff behind, so it cycles through and leaves any pollution behind as it goes up into water vapor and clouds. And then also, as it moves through the earth, flowing water is naturally filtered, whether it's going through, percolating through groundwater, or whether it's moving across the surface and is filtered by bacteria. Water is cleaned. It's great. As with all the cycles we discuss, we're going to talk about the human impact, and how humans are impacting the water cycle is mainly that we just use so much of that available fresh water. And really, if you look at the amount of water on our planet, only about 3% is available for our use. The rest is stuck in salt water or frozen in glaciers. And so what's available for our use, we typically use faster than it can be replenished. And as a result, we're overusing or not taking water sustainably. Another human impact on the water cycle is that we clear plants and replace that area with concrete. And in the course of doing so, it increases the amount of erosion and landslides that are potential, and also it increases the amount of flooding that we see because the water has no place to go. For example, the Hurricane Harvey in Houston, we saw major flooding in Houston due to the amount of paving that has happened of land that would normally absorb that extra rainwater. As a result, we don't get a whole lot of groundwater replenishment, and so we have less available for our use if need be. All right, the next cycle that we're going to cover is carbon. And as we know, carbon is literally everywhere. That's why we call it organic. Molecules are living things, and living things have carbon in them. And so the carbon cycle is just basically a series of processes that moves all carbon atoms in existence through the cycle. And all the carbon on Earth and in living things gets recycled over and over and over again. All right, so first question, where is this carbon that is everywhere? We find carbon as CO2 gas in the atmosphere and air. We also see CO2 dissolved in ocean waters, and in all organic or all living things have carbon as carbohydrates and proteins. And finally, carbon is also, obviously, if it's in all living things, as those things decompose and fossilize and eventually become fossil fuels, carbon is still left over in those fossil fuels and in sedimentary rocks. Okay, the two main drivers of the carbon cycle in living things are photosynthesis and respiration. We know about photosynthesis, and we'll cover the equation next. So during photosynthesis, plants take in the carbon dioxide that we breathe out, and that's in the atmosphere. And they also use water and sunlight energy to convert it to glucose and the oxygen that we breathe. Carbon's in all animals. We get the carbon from what we eat, whether it's other animals or the plants that are naturally photosynthesizing and making that sugar for us. So how does carbon get back into the air? It gets back into the air using cellular respiration. All living things give off CO2, whether it's plants or animals, and it's the opposite equation from photosynthesis. So in this case, just like as we go through respiration, like plants and algae and all living things, we take in oxygen and glucose, and we produce CO2 and water and some energy, luckily for us, in order to breathe and eat and move. Okay, as living things die, we break down those dead things. Decomposers break them down, and the carbon in those dead organisms either goes off into the air as methane gas and CO2, or back down into the soil where they either fossilize or are used as nutrients in the soil. Speaking of carbon turned into fossil fuels, it requires a lot of the perfect conditions for this to happen. But in organisms that are buried, especially in anaerobic or oxygen depleted areas, you see these organisms over many, many, many years, they eventually will turn into coal, oil, or natural gas, and we call those the fossil fuels. There's a great video on the website if you want to check that out for how fossil fuels are made. So how does CO2 get back up into the atmosphere? There are a number of ways. We talked about decomposition, but also through power plants and factories and homes as we emit carbon. Also the burning of forests, either with forest fires or slash and burn agriculture, and also combustion engines with cars and trucks. So how do we get CO2 out of the atmosphere besides photosynthesis? One way is through the gas exchange between the air and the ocean. And over time, the ocean essentially absorbs the CO2 from the atmosphere, and it can sink down. There's a huge storage of carbon here in our oceans, and another big reservoir for carbon is sedimentary rock and the sediment at the bottom of the oceans. We'll talk more about ocean acidification in the next couple of weeks. So what is the geological part of this cycle? Where is the carbon on Earth? In sedimentary rock, right? The biology part of the life part of this cycle is photosynthesis and respiration, going in and out of living things, and as we decompose, going back up into the atmosphere. Again, the major reservoirs for carbon are in our oceans and sedimentary rock, down in fossils and becoming fossil fuels, and then in life on Earth. Major human impacts on the carbon cycle include when we burn fossil fuels, the carbon in them is released into the atmosphere as CO2 primarily. Our carbon dioxide percent in the atmosphere, or parts per billion in the atmosphere, has increased dramatically since the Industrial Revolution. We also release carbon as we burn trees. That carbon goes back up into the atmosphere. And as we know, photosynthesis is a main way that we get carbon out of the atmosphere. So if we remove trees through clear cutting or other clearing of land from vegetation, we're taking the amount of CO2 that could be removed during photosynthesis out of the picture. So again, we get carbon into the atmosphere. Every living thing, we give off CO2 through respiration. When we burn organic matter like wood, some people have wood stoves in their homes, or during forest fires, the burning of fossil fuels like coal and oil, and then through decomposition as well of dead plants and animals. So how does carbon get out of the atmosphere? It can get out of the atmosphere through photosynthesis and also through the absorption of CO2 in our oceans. All right, the nitrogen cycle is very complex, so we're going to try to make it as simple as possible. All right, there are three major ways in which nitrogen moves through its cycle. The ones that I want you to focus on are nitrogen fixation, nitrification, and denitrification. Another one that we'll look at is ammonification, all very important for the nitrogen cycle. So just like with carbon and water, where is the nitrogen on our planet? Well, the major reservoir for nitrogen is the air. In fact, 78% of our air that we breathe is nitrogen gas. However, we can't use that nitrogen gas. Most organisms have no ability to use that, so it has to be fixed in order to be usable. There are two major ways that nitrogen gets fixed into a usable form. The first is through lightning. About 10% of nitrogen is fixed through atmospheric processes like lightning, that heat and pressure breaking those triple nitrogen bonds. And about 90%, the big way that nitrogen is fixed, is through bacteria. Bacteria, again, is the driving force for the nitrogen cycle. Nitrogen-fixing bacteria, a lot of them are found living in the roots of specific plants like legumes, alfalfa, clover, soybeans. The bacteria live in those nodules of the plants and they fix the nitrogen into a usable form. The usable form for nitrogen is nitrate. A good way to remember that is the plant ate nitrate. And nitrate is really what plants can use and absorb the major form of nitrogen. Also ammonia, but less usable for plants than nitrate. So first, nitrogen-fixing bacteria fix the nitrogen from the air and bring it back to the soil. And then, once in the soil, special bacteria help through the process called nitrification to convert the form in the soil to a usable type of nitrate that plants will happily take up. So why does all this matter? Who cares? Nitrogen-fixing bacteria on plant nodes, and then the nitrification happens and plants can use that nitrogen. Well, ironically, the limiting factor for plant growth in the soil is actually nitrogen. Even though so much of it is in the air, very little of it is actually usable by plants until bacteria are there to help. So as a result, we have to fertilize plants to get the success we need with them growing. In order to have success with plant growth, farmers and gardeners often rely on these commercial fertilizers for their crops. Another method is by crop rotation, so that they plant specific nitrogen-fixing plants in one area that fix the nitrogen into the soil, and then plant on top of that with things like corn in order to have rich soil regardless of where they are. Unfortunately, we often over-fertilize our crops with the hope of the desired effect for those nitrogen-needing plants. Once plants are able to take up nitrates, and they convert them into amino acids and nucleic acids and vitamins, and certainly all living things need nitrogen in order to survive. We acquire our nitrogen from the plants we eat or the animals that eat the plants. All living things obviously need nitrogen. Plants use nitrogen for important molecules like proteins, nucleic acids, and the DNA. And it's also for other major cellular components. So animals eat other animals that eat the plants, or animals directly eat the plants that have processed this nitrogen for our use. And then when the animals and plants die, the nitrogen's released back into the soil by decomposers. And guess what? Decomposing bacteria. This is known as ammonification, one of those four processes. So more on ammonification. These animal waste products are also return nitrogen to the soil. So when we pee and poop, the urine from the animals creates excess nitrogen in the soil oftentimes. And also, like I said in the last slide, when organisms die, that nitrogen returns to the soil. So the last part of the nitrogen cycle is how we get it back into the air. And it's a process known as denitrification. And again, what do you know? Bacteria, known as denitrifying bacteria, act on nitrate molecules and put that nitrogen back into the air as nitrogen gas. Something happened with my slide here, but that says human impact. The major human impacts on the nitrogen cycle, first off, is the burning of fossil fuels. You can't really see that, but that puts nitrous oxides into the air and eventually can lead to acid rain, acid deposition, and also smog in the air near these industrial plants burning fossil fuels. Another major issue with human impact on the nitrogen cycle, which we have talked about in class, is over-fertilizing plants. And as a result, sometimes the plants don't soak up the nitrogen in the fertilizer, and that nitrogen leaches into the soil and eventually into our watersheds, where it gets taken up happily by those plants from runoff. And as a result, the plants in the water, the algae, have major algae blooms sometimes, as we see here in both of these images. So as in the last slide, just as nitrogen acts as an excellent fertilizer for crops, it also can fertilize aquatic watersheds, this being the Mississippi River Delta here, and major algae blooms here in the spring in the Gulf of Mexico. The problem with that is the algae takes up so much of the oxygen that other organisms don't have the oxygen they need to survive. This can lead to dead zones like here in the Gulf of Mexico, off Chesapeake Bay, and we even have a dead zone off the Pacific coast near the Columbia River. Another way that humans have impacted the nitrogen cycle is with the nitrous oxide that's produced and put back into the atmosphere when bacteria feed on animal waste, and fertilizer also lets off this nitrous oxide. Nitrous oxide happens to be a really powerful greenhouse gas, and while there's not a ton of it in the atmosphere, the amount that's there is really impactful, and it also now is known as one of the worst ozone depleters left in the atmosphere. All right, so here are your first two questions of the day, and I'd like you to write this on a separate sheet of paper. What's the driving force of the nitrogen cycle? And what are the four main processes that move nitrogen throughout the nitrogen cycle? The next cycle, which is actually probably the simplest, luckily, is the phosphorus cycle. And the phosphorus cycle I like because it doesn't have an atmospheric component. Woohoo! What we do see with all of the cycles is the plants absorbing these nutrients, animals eating those plants or eating other animals that eat those plants, animals peeing and pooping, and the decomposition of those plants and animals by fungus, and then the reabsorption of those nutrients by the plants. So this is the cycle that we see throughout all of the cycles. We also see loss of those nutrients into the water, and it's called leaching out into water. So phosphates that aren't absorbed or end up in the soil can leach through water out into our watersheds, just like nitrogen can and carbon can as well. All right, the major difference in the phosphorus cycle compared to the other cycles that have a gas, liquid, and solid phase, phosphorus has no atmospheric component. You just don't see phosphorus up in the air unless it's in the solid form of dust. It also tends to be a very slow and local process, so the phosphorus isn't moving or very far. It's weathering from rocks and pretty much staying put, but it takes a very long time for phosphorus to go through the cycle. The major reservoirs for phosphorus is sediment, and it's stored in rock sediment. It's released through weathering and erosion, which takes, like I said before, a long time. Once it's released through weathering and erosion, just with wind, rain, snow, heat effects, the small amount of nitrogen, along with the liquid rain, gets moved down into the watershed and eventually is taken up by plants through the soil. So what about humans? How do we get our phosphorus? Again, all consumers get their phosphorus from the food they eat. It's absorbed from the soil by plants, and it's used in the building our bones and teeth and our DNA. So super important phosphorus is for us and other animals and plants. Decomposers, of course, when things die, decomposing bacteria, mushrooms, slugs, you name the decomposer, help to return that phosphorus back into soil and potentially into water by breaking it down. Phosphatizing bacteria specifically are important in converting phosphorus into other usable forms for plants, like phosphate. Think the plant ate phosphate, just like with the nitrogen cycle, the plant ate nitrate. Phosphorus is often found in the waste products of fish-eating birds, and so their poop, known as guano, is really high in phosphorus, and it contributes a little bit to the cycle as it weathers off this rock or becomes sediment. So weathering and erosion, we talked about moving it from its major reservoir of sedimentary rock, and then that rock, if it gets caught up into the water of the weathering, gets moved sometimes into the ocean, and there it can sink to the bottom of the ocean and become sediment at the bottom of the ocean, and there it can get trapped for a really long time until something disturbs that sediment, and it then gets moved upwards through geologic uplifting, it's called, and that's where eventually it'll become part of the weathering process again. So human impacts on the phosphorus cycle. The main problems associated with the cycle are that we use it, just like nitrogen, in fertilizers. And in order to get it to use in fertilizers, we've resorted to mining it for fertilizers. And just like in the nitrogen cycle, too much phosphorus can eventually leach out of the soil if it's not used by the plants and contribute to what's called eutrophication. And that's when waterways are essentially fertilized and you have these algae outbreaks, also known as algae blooms. Again, another picture showing the movement of phosphorus through the cycle. And another picture. All right, your third question for today. What are the major human impacts on the phosphorus cycle? And our final cycle is the sulfur cycle. Most of the sulfur in the sulfur cycle is stored underground in rocks and minerals. So we don't really see the majority of the sulfur moving through land, water, air because it's buried in rocks. All right, so how do we get sulfur up into the air? One way is through volcanic eruptions of sulfur. Here you see. Another way is decomposers in really wet ecosystems. Normally these decomposers don't need oxygen, so they're called anaerobic decomposers. And they're in swamps and wetlands and bogs. And you might have been to these areas and smelled sort of this rotten egg smell. That's the hydrogen sulfide that you're smelling of the decomposition and that sulfur moving into the atmosphere. Another way not listed here is the burning of fossil fuels. So combusting fossil fuels, really high intensity heat to make this suffocating sulfur dioxide, which then will become acid rain. Or I should say contribute to acid rain. So completing the cycle, bacteria in low oxygen environments convert sulfate ions to sulfide ions, and sulfides react eventually over time with metals to make metallic sulfides, which form these rocks. So now we're back into the ground. All right, so sulfur, just like phosphorus and nitrogen and carbon, is super important to all plants and animals. And in fact, they make up some of the proteins and vitamins that we need in our diets. Plants, just like with the nitrogen cycle and the phosphorus cycle, absorb sulfur through their roots. And then, of course, animals get sulfur by consuming plants or consuming animals that have consumed the plants. Okay, so finally, how do humans impact the sulfur cycle? The number one impact is that we burn fossil fuels of coal, oil, and we refine petroleum. And in doing so, sulfur is released out into the atmosphere. Another way is we convert sulfur containing ores into metals like copper, zinc, and lead. And in that conversion process, also sulfur is put out into the atmosphere. All this sulfur in the atmosphere eventually leads to what's called acid deposition or acid rain. So as depicted in this image here, we see that sulfur dioxide burned in industrial processes leads through a reaction with water and becomes sulfuric acid. Nitrogen oxide, also the burning of fossil fuels combined with water and precipitation in the clouds, forms nitric acid. And combined, all of those can lead to acid particulates and gases falling as acid snow or acid rain. You may not have even heard of acid snow, but certainly in the Northeast, that's a problem. Another image showing those sulfur dioxide and nitrous oxides and the particulate matter from industrial pollution or fossil fuel burning, leading to these emissions, and then what's called deposition. And then the effects of the deposition are that we end up with acidic watersheds like lakes and ponds, and it can also impact buildings and structures because we know of a pH below 7, and most of the time rain is actually below 7 naturally. But once it gets into the 5 zone, it becomes really harmful, and as it accumulates, that rain-fed aquatic systems become more and more acidic, and life can't handle those acidic environments.